Thank you all for being here today to listen to this presentation on my work from the past 3 years on mapping forest heights and biomass at high resolution in France with satellite remote sensing and deep learning. You probably don't know this person, but she's responsible for a fourth of the French forests. She's the head of the Office National des Forêts, which is the organism that manages public forests in France. And being at the head of the ONF is quite a challenge for several reasons. The first reason is a climatic reason. As you know, with human activities, we emit fossil carbon dioxide from the burning of fossil fuels. And this carbon dioxide creates the climate change. And the forests have this ability to capture carbon dioxide, to store it in the form of carbon in their trunks, leaves, and branches, and to mitigate climate change with this. So this CO2 absorption, CO2 is carbon dioxide, is a big issue, a big matter for the French forest, and there's and that's why it's a big, it's very important, a very important issue for the French forest. The second big challenge that is at stake here is the wood production. As you know, we produce wood, forests give us wood for construction materials, for heating, etc. And in France, the wood production, the harvest of wood has increased by 20% in the past 10 years. But the growth of forests has decreased by 10% also in the past 10 years. So you see both trends are very opposite at that time. And so there's also a big issue here when you have to manage the French forests to combine this CO2 absorption and wood production. But also this person also has to face other issues like attacks of insects, like bark beetle attacks, or fires and storms that will affect French forests. And that increased the mortality of trees in the French forest by 54% in the past 10 years. So how to monitor the French forests, how to follow the state of the forest and to have a management of the forest that will combine this CO2 absorption, these wood production objectives, and protect the forests. I took this photo last summer when I was hiking in the Ardennes region with my sister. And actually, there's something I want to show you here. This is the fact that the French forest is divided into small parcels of several hectares, but very small parcels. And you can see on this picture that the parcels are very different. You have different management types, different type of tree, different. You have broadleaf tree, coniferous tree, different densities. And if you want to manage the French forest to meet these objectives of wood production, carbon absorption, etc., you need to have a management which is at the scale of this parcel. So basically, we'll need maps that will show forest attributes at this level. And this is what this PhD is about. We'll map forest height and biomass that are forest attributes that are related to forest management, but also this stock of carbon into the forests in France. So here's a satellite image of also a place in France, in the Loire region. And if you are, for instance, this person who's at the head of the ONF and you own this forest, or maybe you also are one of the 3 million forest owners in France, and you want to have information on your forest resources to do proper management, or maybe evaluate the damages that could have happened following insect attack or storms or fires, you will need a map, as we said, but not any map. We'll need a map that will have a resolution which is sufficient enough to monitor this forest. And this is here why I chose to work at high resolution, because in France, this is necessary if you want to monitor the forest. Because you can see that above 50 meters, it's not possible anymore to monitor that forest. So now we're going to see the second part of this title, how scientists have done to create such maps, and what did I bring with this PhD to improve them. So how do the scientific community create such maps? The first thing is the variable used, and the main ones are height and biomass, the ones I presented already. So height is basically the height of the trees, and biomass is the weight of the trees, and this is correlated to the carbon content. So having maps of biomass is basically having information of where the carbon is stored into the forest. And to do these maps, we need images. And these images comes from remote sensing data, remote sensing imagery. And the main, so that comes from satellites or airplane sensors. And the main two types of imagery are optical sensors and SAR sensors. So SAR means synthetic aperture radars. Optical sensors are sensors that are passive, so they measure the sun's reflected light in the visible and near infrared spectrum. And it's basically as if you were taking a photo from a plane or from space. SAR sensors are active sensors. They send a microwave on Earth, and this microwave is reflected on the trees, on the branches, etc. And then we can get an image from this reflection. It can operate at day and night, and it can see through clouds because of this because it's an active sensor. And so both type of sensor have their pros and cons, and combining them can be interesting to map forests. So how to do this kind of maps with this remote sensing imagery that I presented? The first idea is to find a correlation between the value of the pixel of the image and the value of measurements that can be made directly on the ground. So in this study from IMOF in 1995, the author tried to correlate the biomass of forest inventory plots, so people measuring the trees on site, and the backscattering coefficients of a P-band SAR, which is a sensor, a SAR sensor, and the backscattering coefficient is basically the value of the pixel. And they obtained this. So if we look at these white squares, we can see, so these white squares represent one of the backscattering coefficient, the horizontal backscattering coefficient for coniferous forest. And you can see that above 100 meter, the sensor doesn't see any difference between the different forests with different biomass. And this is called a saturation effect. And the question that scientists try to answer is how to overcome the saturation effect, to create maps that are coming from this kind of images. So this effect has been seen in many studies, both for optical and for SAR sensors. And to try to overcome this kind of effect, different techniques have been used. The first one is to use multiple data sources. So if you combine optical sensors and SAR sensors and other types of sensors, you can have a better effect to predict this kind of variables like height and biomass of forests. The second idea is to use machine learning algorithms. These are algorithms that will better combine the different sensors in a more efficient way than just doing a correlation. The first study that did that were operating with satellites at a resolution quite moderate, not the resolution that we're targeting in this PhD, but these were the first maps. And the one in green here are the one that did high prediction, and the one in brown are more also predicted biomass. And then if you go later, there are other studies with the resolution which is higher, just because they are based on sensors that have a higher resolution. So all these studies implemented these two techniques. Other techniques that were used to overcome the saturation effect is to take more from the image. Instead of taking the value of the pixel, you take texture indexes that are basically you look at not only the value of the pixel, but also around the pixel. And this texture on the image can give predictive information to have the height or the biomass. So some studies also did that, but to do that, you need a higher resolution. And we can, for instance, cite the study from Peloton et al. That uses Pleiad images that have a 1 meter resolution and to predict biomass in Africa. And then more recently, there are new advances in forest remote sensing that I want to present here and that are correlated to my PhD. The first one is the arrival of new algorithms that are called CNN, deep learning algorithms. So these algorithms have been invented a long time ago in the machine learning community and deep learning community, but they arrived really recently in the remote sensing and especially in terms of forest remote sensing community. And the principle of these algorithms is that they they can leverage much more the input image to create, to have a predictive information, especially when you have a lot of data. And the first study in this field that used such models is the study of Long et al. In 2019 that published a map of Switzerland and Gabon at 10-meter resolution, and that showed very promising results. In parallel to that, you have new sensors. So the two first one I want to show you are Sentinel-1 and Sentinel-2. These sensors are part of the ESA's Copernicus mission, so the European Space Agency. They have a 10-meter resolution. Sentinel-1 is a satellite that hosts a SAR sensor, and Sentinel-2 has an optical sensor, and they have a frequent revisit interval of a few days. So every 5 days, you have a new image of Sentinel-1 and Sentinel-2 everywhere in the world. They were launched in 2014 and 2015, and actually you can see the study from Morin et al., Chen et al., and Long et al. Uses these sensors to do these 10-meter predictions maps. And the last one is JEDI. So JEDI is a space-borne LiDAR, so the principle is that it sends infrared light on Earth, and it captures information about the forest structure. So it's not the first one of its kind. Before JEDI in 2018, that was mounted on the International Space Station in 2018, there was ISAT, the glass instrument on ISAT in 2003, and its little brother ISAT-2 in 2018. And most of the study you see here on the left are based on ISAT to have height measurements. So how does JEDI work? It's quite simple to understand like that. You have a satellite that sends, so the sensor sends infrared light on the forest. It's reflected on the leaves, on the branches, on the ground, on different parts of the tree. And then you have a waveform that is captured because of the reflected photons, and that gives us information about the vertical forest structure. So you can see here, when there's a bigger part of the tree, you have a higher return of the waveform. And from that, you can extract the height of the trees, the canopy height. So here is an example of the forest of Crécy in the Somme department. And when you look at the JEDI measurement on this forest, you have this. So you have all these little points that represent forest height measurements. And so that's in this context that my PhD started in September 2020. And so at that moment, there were no study using JEDI to create height maps. And there was only one study in this field using deep learning. So we thought, why not using deep learning and JEDI, that was not done at that time, plus these new Sentinel-1 and 2 images to create high-resolution tree height maps. And this is what I'm going to explain you here. The first part is going to be about creating these height maps. The second part will be about how how I went from height to biomass with these maps, because biomass maps are also very important. And the last part is going to be about how, applying this model to several years, we can have estimation of the carbon fluxes because we can have height changes. So let's focus on the first part. How to create this high-resolution height map. So the idea we wanted to do is to have these Sentinel-1 and Sentinel-2 images, to put them in this new deep learning CNN algorithm, and to obtain a height map. So to do that, we need to understand what is this deep learning CNN, and particularly what is a convolution. So what is a convolution? It's a very simple mathematical operation. The principle is that you have a source image that you will see on the left. Then you have the convolution kernel, which is a 3x3 grid of number that you will apply to the left image to obtain a new image by combining the pixels. So if you see here this sliding window, gray window, it combines all the pixels and it gets a new value. So it's a linear operation between the pixels, nearby pixels, and thanks to that, you can extract information that are relevant and that are spatial information. So If you apply it to this image that you have on the left, if you apply, for instance, this convolution kernel, you will highlight the edges of the image. If you apply another convolution kernel like this one, you will highlight something else and get another image. And then you can do it for another convolution kernel and highlight something else. So you can see here from only one image with 3 convolution kernel, we can extract 3 very different things that can help us to do height predictions then or biomass predictions, because it extracts important information from the original image. So now that we understand what is a convolution, let's understand what is a convolutional network, deep learning, a CNN. So a convolutional neural network is a series of convolution. So it's just, so let's do a simple convolution network to understand how it works. So we have our image, we put our 3 convolutional kernel like that. Then we also add activation functions that are nonlinear, that are important to give nonlinearity to the model. And then you have these 3 images. You can also put another convolution kernel like that, and you have your output. So this is a simple CNN, and we can represent it this way, with 1 layer, 3 layer, and 1 layer, and the arrows represent the convolutions. So what we wanted to do was to obtain the height from this image that you have on the left. So to do so, to have this forest height, you see, the only thing you can do is to modify the values that are in the convolutional kernels. So these values are called the weights or the trainable parameters. Here you have a model with 54 weights. And you see that if you modify it, you will have a different output. So doing so is, we can do this by a training process of the model. So we will compare the output of our model with the footprints of Jedi. So the Jedi footprints, they give the height, as we said before. So this is the reference value. And we compare the output to Jedi. And then we calculate something that we call a loss function. That is a function that tells us how far we are from the reference value from Jedi. And then thanks to this loss function, we can adjust the weights through a phenomenon that is a process that is called loss backpropagation. And this is possible due to the calculation of the derivative of this loss with respect to each of the weights of the model. And then we can adjust the weights so that the loss will decrease. So if we do that a high number of times, for instance, so we take another image on the left, another reference Jedi footprint, then we do that a high number of times. At some point, the loss function will decrease step by step. It's a stochastic process. And at some point, the value of the weights in the kernels will be the optimal value, so that when you put on the left this image, you will have on the right the height prediction. So this model is very simple. It has only 54 weights, and it will never be able to extract this height information from the image that you have. So the model we use looks like that. It's a much more complex model. It's called the UNet model because of this shape of a U shape. And it was designed in 2015 for biomedical image segmentation. And it outperformed most of the classical machine algorithms for many tasks, especially when you have a lot of training data. And it can learn from multi-scale image texture and context. And this is basically because of this U shape, where you can have convolution that are made at different scale on the image. You see when you reduce the size of the image, this is like here with these orange arrows, we reduce the size of the image with a max pooling operation. And doing so, we can, the convolution that we calculate on these new images, it's like calculating a convolution on the broader part of the image, and then it gives context to the model. And this model has 17 million of weights. So compared to the one before, it's much more complex, but this is such model that will be able to extract the interesting information and get this height and biomass. So now we have our model. We know how it works. Let's process a little bit these images. So to do so, we took a median composite cloud-free image for the leaf-on season. Basically, we took all the images that we had of Sentinel-1 and 2 in the summer, and we averaged them into a median average. And this is how we obtain our data. And then we train the model. So to do so, we replace the simple CNN by this unit model. And then the input is also not just a single black and white image like that, but our 14 bands from Sentinel-1 and Sentinel-2. So we have 4 bands from Sentinel-1 and 10 bands from Sentinel-2. So we took these bands from different places in France. So we have France, we divided it into test, train, and validation area. And in the train area, we randomly select a place. We have our images, and then we put them into the model, and we do this process with the backpropagation, etc. And we do that a high number of times, like 10,000 times, to minimize the loss. And this is how we train the model. And at some point, the loss function will reach a minimum, which indicates us that we cannot train it more, and that the filters inside, the convolutional kernels inside, are the best for this task of predicting height. And then we have a model that is able to carry out height predictions. So I won't go further into this methodological part. And now we'll go to the parts of the results. So we will see what are the outputs of this model and how does it work. So we first focused our study on the area of Les Landes. So this is the forest of Les Landes in southwest of France. It's a maritime pine forest of 1 million hectares, highly managed forest. And we had this height map for the year 2020. And then, because we saw that it worked very well, we extended this work to the national level. And so you have this map of France at 10-meter resolution. And so where you see, where the map is brighter, when it's more yellow, it means that the trees are higher. So you can see the Vosges mountains on the top right place of this image here. The trees are higher than in other regions. If you have a closer look, we zoom in. Here is an image from the satellite Sentinel-2, and you can see, so we are here in Yonne, and this is the height prediction we have with our model. So you can see that you have different forest patches, different sizes of forests. Here you have a very big forest. Here, like very tall trees, I mean. You can also see so visually it seems to work. Here, and so we call our model the Forms H model, which means forest multiple satellite height. And this is how we're going to call it for the rest of the presentation, because it was done in that's the name we gave it into the publication. So if you remember those JEDI measurements, all these little points, so we went from that to this, which gives us much more specialized information and much more interesting insights on the forest than just the value of height from JEDI. Here is another example from the picture that I saw at the beginning. If you remember, you had these little parcels of forest, and this is the prediction. And you can see that it corresponds well. You have these parcels of forest that are that corresponds well, and you can see also that the height corresponds. And even here, you can see that it seems that there's a place with the height which is lower, which has been captured by the model. So this is only a visual understanding of the results, but how to validate that? So to have a quantitative validation, we compare that to several data sets. The first one is the National Forest Inventory data. So it's data that are collected by the IGN, so the French Forest Inventory Service, and the people go on the plots, and they will measure the height of the trees and different other things. And here we compared our map to this data set. So on the x-axis, you have the NFI plot, so the value of the height from the plot data, and on the y-axis, you have our map. And this is the output this is the scatter plot we obtain. So here you can see that we have a R2 score or 0.69, a mean absolute error below 3 meters, so which is quite good for this kind of height predictions. But you also can see that there's an underestimation of the higher heights here. Above 30 meters, you can see that all the heights are below what it is supposed to be in the forest inventory. And we observe also this trend when we look at other validation data. So we compared here to airborne LiDAR data, which is a very highly precise way to measure the height from a plane. And it's also from the IGN here, in a region north of Paris. And we have this scatter plot, which shows exactly the same trend with the same error metrics and also the same underestimation of higher heights. So what I didn't say in the beginning of this presentation when I did this timeline is that I was not the only one that had the idea to work with JEDI to create these height maps. And so here I would like to introduce 3 other studies that did also height maps. And the first one is the one from Potapov et al., which is a study that mapped globally the height at 30-meter resolution using the Landsat satellites and JEDI. The second one is the study from Long et al. That mapped globally also the heights at 10-meter resolution using deep learning algorithm JEDI and Sentinel-2. So it looks a lot like what we've done, and so it's interesting to compare to that. And the last one is a study from Liu et al. That mapped forest height in Europe at 3-meter resolution with planet data, so it's private data, and airborne LiDAR, and also deep learning algorithms. And that's also interesting to see how our model compares to those type of data. And the last one also, this study from Liu et al. Also provide a biomass map at 30-meter resolution that we'll see after. So my study arrives at this moment, and it's interesting to see how does it compare to these other studies. So here's a visual comparison of the model. My model is the one on the left, and the 3 others are here. And so at first glance, it's not easy to see which one is the best because we can only see some things about the resolution. And maybe the one on the right, the Potapov et al., we can see that they could not really predict the differences in terms of forest parcels that the 3 other seems to capture. Now, if we have a quantitative look on these results, we can see my map on the left and the 3 other ones ordered in the same way. And the first thing you can see is the comparison with the ALS data that I showed before. We can see directly here that we have better validation metrics, and also that the 3 other maps have less good validation metrics, but the one from Liu et al. Is quite good as well. Long et al. As well has an overestimation of the lower heights, and the one from Potapov et al. Seems to be a bit less correlated to these validation data. So why we have better results? There could be 3 explanations. The first one is maybe we have a better deep learning model, but maybe also it's because we have these SAR data, synthetic aperture radar data, that the other don't use. And the last explanation could be that we are working at local scale. I mean, local at the national level in France, while the other studies have a much broader extent, and this could be maybe more complicated to be validated in France for those studies. So that was the part about height mapping. So we have this height map. It works well, has good validation metrics, and it's better than the others, but still this underestimation of higher heights. And now we'll go to a second part of this presentation about mapping the biomass of the trees. And for that, we'll use a method that will convert the height map into a biomass map. So you see, height and biomass can be related. If you have a tree which is twice bigger, it will be twice more heavy, let's say. But it's not completely correlated because it's like humans. You have tall humans that have different weights. Same for the trees. So how did we do that? First, we correlated the height from our map to the biomass measured by the forest inventory measurements, the one we showed before. So this is for the coniferous forest, and then we fitted a power law allometry equation to that, and we did the same for broadleaf forests. Then we use a map, which is the Copernicus dominant leaf type map, which tells us where the broadleaf and where the coniferous trees are. We combine this map with our two allometry equations that we combined with the height map to convert the map into a biomass map. We just applied this relationship height biomass to the height map, and we obtained a biomass map at 30-meter resolution in France that we called FOMSB. So we here computed this at 30 meter because we thought biomass has more meaning if you keep it at 30 meter in terms of biomass density. And also because the forest inventory plots have a 30-meter size. So how to validate that? So it's more complicated to validate biomass maps because you don't have very precise measurements of biomass like we have with the airplane, or at least it's more complicated to measure biomass. So the first validation is with the forest inventory called the Rennes-Coffort, with the old forest, mature forest, very let's say, complicated forests in terms of structure. And this is what we obtain in terms of validation. So on the x-axis, the value of biomass from Rennes-Coffort. AGBD means above ground biomass density. And on the y-axis, you have FOMSB, so the map I produced. And you can see here that the validation metrics, like the R2 score, for instance, is much lower than for height, which shows that it works a bit less good than for height. If we look at another forest inventory, the GLORY dataset, that is a forest inventory carried out in 2016 in the forest of Leland in south of France. So it's pine forest, managed forest with much lower biomass. We have a much better correlation, but still some points are a bit out of the one here, out of the correlation, and the validation metrics are also a bit less good. And actually this forest inventory has much less biomass, as I said. If you scale it to the graph on the left, you can see that it should be here. So, as I said, it's less good, has height validation. Maybe it's because of this simplistic approach with coniferous and broadleaf, but it's also maybe because there's a lot of uncertainties in the calculation of biomass in these forest inventories, like a 30% error, which makes it more difficult to validate our maps. And now the question is the same as for the height map. Is it better than the existing products? Did we improve something? Did we bring something new to the community? And for this, I'd like to introduce a last study, which is the ESA CCI Biomass Map, the fourth version of it, which is a project from the European Space Agency to map the biomass globally at a resolution of 25 meter. And this is not based on machine learning or anything like that. It's based on soil data and on the physical, let's say a physical based process. So we compare to this map and to the map of Liu et al. That also did this biomass map. And what's interesting is that those two products and our product don't use the same data and the same methods. So it's three completely different products. If you have a visual understanding of the comparison, I always put the same forest so that you start to know this place. You can see that the one on the right shows a bit less correlation to the two that are on the left. And especially here where you have a high biomass and here you don't have any signal of high biomass. So it seems that maybe the two ones on the left works a bit better. And if you have the validation with Rennes-Coffort, the one that I showed before, you can see that we have better validation metrics here. Sorry. Better validation metrics for Rennes-Coffort, but it's quite the same as the one from Liu et al. And if we look at the global forest inventory, it's a bit the same conclusion. We do a little bit better, especially better than the CCI biomass, but not so much better than Liu et al. But still, it's better. The conclusion is that it's better, But there are still large uncertainties at this plot level, and that's why this biomass map is just like, for the moment, a first attempt to map biomass in France. So this is, let's say, the best biomass map, but still have to be improved. There are a lot of way for improvement. So we did that. We had wanted to have information, spatialized information on this forest. We have this forms H map that gives us the height at 10-meter resolution in France, and the forms B map that gives us the biomass at 30-meter resolution, also in France. And you can see that this forest has much higher biomass than the one around, and that was not visible on the satellite image. It was not obvious, at least. So now we move on to the next part, to the last part, which is a part where we try to evaluate the forest height change. So applying the model to different years to see the change in height. And this is very useful for different things. The first thing why it's useful is that you can monitor the growth of the tree, the growth of the forest. So for wood production, for forest management, it's very useful to have this kind of information. But also, if you have the growth of the tree, you can have how much they store carbon from one year to another. So you have your fluxes of carbon. But if you also have the difference in height of the tree, you can also see when a tree falls or when a tree dies, when a tree is cut. So it can also help to monitor the disturbances that can occur in the French forests. So to do that, we adapted the model to predict on different years. I won't go into details here, but the idea is that we predicted on raw images instead of applying it to median averages. We also adapted the loss function to have a better estimation of higher heights. We trained the model with JEDI data from 2019 to 2022, and we did the prediction from 2018 to 2023. But we'll be able to do it from 2015 to 2023 in the next months, when we'll have more data coming from the European Space Agency. And so we only worked on forest height, not on biomass, because of these uncertainties that I talked before, and to see if it seems to work on. So here is the results we obtained. So this is in the forest of Leland because it works very well. So I prefer to show you this example. And you have this little animation where you can see the height that increases year after year, the height that changes from our model. So I want you to look at this forest, for instance, that appears step by step. You can see this is a small forest growing year after year. And here, if you look at this place, you can see that in 2023, there's part of the forest that disappears. So what I said before, monitoring the disturbances is also possible with this kind of approach. If we do the difference between 2023 and 2018, we can see that this forest have grown, so the part in green, and that the other forest has been cut. So this is the part in red. So this works very well. In other regions, it works also well, depending on the type of trees. But we had the idea to try to aggregate this kind of signal at a regional level to see how the trees are growing on average per region. So here is still an example in the forest of Leland in southwest of France, where we took I took on the x-axis the tree height in 2018, and on the y-axis the tree height for the same pixel exactly in 2023. So the first thing we can see is that you have a lot of pixels that are related to people cutting forests, because the land is a highly managed forest. But then if you look at this scatter plot, density scatter plot, you can see that on average, most of the points are located here. So this is the median of this scatter plot. And this median tells us about the signal of tree growth on average in this region. So if you put this median on the graph you have on the right, on the x-axis you have the height in 2018, and on the y-axis you have the difference in height between 2018 and 2023. You can see that small trees are growing faster than big trees. And if you do that for all the years, it's interesting because you see we have have what we expect actually. The fact that the trees from in 2019 were smaller than in 2020, etc. And for instance, if we look at the trees that were 10 meters in 2018, we can see that in 2021, they were about 2 meters higher than in 2018 for the trees that were 10 meters. So this gives us an information on how the tree grows, depending on the height in the forest of Les Landes. But we can do that in many of the, other places. So I will show you here two examples. The first one is the Douglas pine, Douglas firs in the Morvan region, and you can see you have this kind of pattern, and the poplar, you have this kind of pattern, and you can see that depending on the species, you have different patterns of growth. So maybe the Douglas are growing much faster when they are about to be 10 meters. Maybe the poplar are growing much faster when they are smaller, and then they are growing a bit less faster when they are bigger. So as I said, we can also apply that to detect perturbations. And this is on the left, an image of the forest of La Thèse de Buch next to La Dune du Pilat. And you can see in 2022 and 2023, the difference in terms of height. You can see all the forest that disappeared between those 2 years because of the big fires that occurred in France at that time. And so this technique can also serve to monitor the forest perturbations. So, if we want to see the contributions that I brought during this PhD through these 3 chapters, the first one is building a framework that combine high-resolution satellite data and deep learning to predict height in France at 10-meter resolution. So we got this map with a 3-meter mean absolute error that is better than existing products. Then we have converted this map into a biomass map, which is better than existing product, but with saturation about 350 tons per hectare, and a lot of high uncertainties still that have to be resolved. And finally, what I just showed, the application to monitor height changes that shows a lot of promising results to understand the growth dynamics of the trees, also to work on the carbon sink and to monitor the forest disturbances like the fire next to La Dune du Pilat that I just showed. All this work led to several publications. The first one is the publication on the forest of Les Landes, that is still in review in the International Journal of Applied Earth Observation and Geoinformation. And this is where I developed the model and tested it on this small region for validation. The second one is the extension of this work to France, and that is published in the Earth System Science Data Journal. And then my map was used in different studies. The first one is a collaboration with Lilian Vallée and Florent Mouillot from the University of Montpellier that was published in Biogeoscience. We used this map to estimate the loss of biomass due to the fire in 2022. Another example of the use of this map is a work that was just submitted by, which is in review in Annals of Forest Science by Agnès Pellissier-Talon, where we estimate the growth of tree after disturbances based on my map and a map of disturbance. And the last one is a study that was just accepted in remote sensing of the environment by Ibrahim Fayyad, where he replaced my UNET model by a model of vision transformer, which is state-of-the-art in deep learning, and that showed promising results. So if you want to improve the model and for the future of my research, there are several points I would like to mention. The first one is, I think the most important one is have a reliable uncertainty quantification at the pixel level, because this will be used, if you want this to be used for by policymakers, etc., we need to have a real uncertainty estimation at this level for this high resolution. Then we could also improve the model and the way we process the data, like changing to this vision transformer model, or to add other filters in the JEDI data and also in the data Sentinel-1 and Sentinel-2 pre-processing. Something else is also to use other sensors, like especially the biomass sensor, which is going to be launched soon, and which is a P-band SAR that maybe have better ability to capture forest biomass. And then something else is to have a better biomass estimation. So as I said, this biomass estimation was really simple. We used this allometry between for broadleaf only and for coniferous. But if you compare two broadleaf trees, actually they don't look the same. On the right you have a poplar, and on the left you have this oak. They don't have the same biomass, even though they have the same height. So maybe using a height biomass relationship for each species could be better. And another idea would be to use more from the Jedi waveform. So we extracted only the canopy height, but if we take other metrics, we could have more information on the biomass, and this is what is done at the by the NASA with their product of biomass, and so that could be interesting to use this product. And the last perspective that could be done here with this project is to go global. And it started with the collaboration with Kairos, a French company, to have a large-scale estimation of with my methods of canopy height and biomass to monitor the conservation in tropical forest conservation projects in tropical forests. And this is a height map of the Congo Basin based on my method. And this is a validation scatter plot. You see the validation is not the same, but it's still quite good for tropical regions. And then another collaboration with Jan Pols and Fabian Giesecke. So Jan Pols is a master student that I supervised during my PhD, and now he's doing a PhD and he's doing this global height map with the same method. And he created this global height map at 10-meter resolution. And actually, it works quite well. And when you look at a closer level, always on this same forest, you can see that the visual quality seems to be quite good. So we still don't have validation metrics, but it shows that maybe the why my model was better was not related to the fact that we worked at local scale. So we're coming to the end of this presentation. Thank you for your attention. I'd like also to give a special thanks to all these people that helped me a lot during my my work, and especially to Aurélien de Truchis from Kairos that also worked a lot with me developing the model and helped me a lot during my PhD, and to the whole biomass team of LSTU for the collaboration on the work we did together. Thank you.